Thank you for joining this session of Shadow the Scientist. I'm your session host, Jamika Marshall, the Shadow the Scientist Program Manager. The Shadow the Scientist initiative is brought to you by a fantastic team at the University of California, Santa Cruz, and we are funded through a generous grant from the Heising Simons Foundation. As a reminder, this session is being recorded and will be posted on the Shadow the Scientist YouTube channel. We welcome questions and comments in the chat at any time throughout the session. And we do invite you to introduce yourself in the chat and let us know where you're joining us from. Now, you're in for a very special session. Now, if you're a Star Wars fan, then you are familiar with Tatooine, the iconic twin sun planet from Star Wars. Now, worlds like Tatooine are no longer confined to science fiction. They've entered the realm of modern astrophysics. These distant worlds, orbiting stars well beyond our sun, are known as exoplanets. At the Subaru Telescope, a powerful instrument called the Subaru Coronagraphic Extreme Adaptive Optics, or SCExAO, enables the direct imaging of these alien worlds. In this session, we will join Dr. Garima Singh, the SCExAO instrument scientist, along with other core members of the SCExAO team, who will offer a sneak peek into the SCExAO observations of an extrasolar world captured by the Subaru Telescope. The team will explain the methods behind these observations, which are actually similar to those used by the James Webb Space Telescope. I'd like to go ahead and welcome our first and main science host, Garima Singh. Welcome, Garima.
Hello. Thank you for the introduction, Jamika. Very happy to be here. I think I'm gonna start sharing my slides and present everybody who is here in the control room. So let me share my screen and please tell me if can you see my screen?
I can see your
Okay.
screen.
Okay, that's good. Well, Jamika, thank you. You've already given the introduction, so I don't have to wait. This is the session with SCExAO instrument. And let me go ahead and actually present all the presenters. So we have Hashimoto-san, who has joined us from Mitaka office from Japan. It's his observing night, by the way. He's the PI of the observing program that we are observing today. And I just realized I've used the word observing 3 times in less than 30 seconds. So basically, Hashimoto-san has wrote a proposal and has gone through basically a proper review process, and he got this a couple of hours of observation with Subaru Telescope to do the science that he will talk about in a few minutes. So he's joining from Japan. Then we have a couple of us joining from the Hilo Base facility. So we have Sebastian. I don't know if you can see him, but so Sebastian will be my co-pilot. He will he will help me explain what are we doing today exactly with SCExAO observation. We have Kumiko-san, who is an astronomer at Subaru. She is helping us here to do the translation from Japanese to English, if there are questions in Japanese. Then we have Olivier Guillaume, who is sitting on my right side. He is the PI of the SCExAO instrument. So he's a brainchild of the SCExAO instrument. And then me. And we also have a postdoc who worked with us on SCExAO, Sandrine. I don't know if you can see her. I don't think you can see the screen, but there she is. And from the Subaru Summit facility on Mauna Kea, we have Julien Lozzi joining us. He is basically the backbone of SCExAO. And then we have Ian, who is the night operation assistance tonight. So if you have any questions related to how the telescope is being operated, he can basically answer all of those questions. So let's begin.
Yeah,
Some of you may not be joining from the from Hawaii, so just a brief introduction where we are. So we are basically on the big island of Hawaii. So it's a chain of Hawaiian islands, roughly 4,000 kilometers from the coast of California. So we are, can you see my, I don't see my mouse. Okay, sorry, I don't think you can see my mouse.
Yeah, that's
Oh,
okay.
okay. All right, well, there's a big island here. So there's a mountain called Mauna Kea. It's a sacred summit of Mauna Kea, which is shown in the lower left side, this image. And on top of Mauna Kea, we have a bunch of telescopes. And Subaru Telescope is one such telescope. The diameter of the telescope is 8.2 meters. And on the rightmost side, the image that I'm showing, basically that's how the whole structure of the telescope looks like. The total height of the telescope is it's 73 feet. And just a fun fact, the telescope structure weighs 612 tons. And it's basically the combined weight of at least 153 Asian male elephants. I found it's a funny fact. It's fascinating, basically. So, um, so yes, so basically we can have instruments installed at the lower underneath the primary mirror in the image which you're looking at top right. But sometimes we can also install instruments on the side of the telescope. So that's the image which is shown in the lower right. So you kind of like see two platforms on either side of the telescope. So these are called Nasmyth platform. So in the instrument that we gonna talk that we are actually presenting today is it sits on one side of such a platform, and there's a little human over there to just kind of give you the scale of how giant now this telescope is. So the science motivation for tonight is, of course, exoplanets that Jamika mentioned. So exoplanets are basically the planets that orbit stars other than the sun, other than our sun. So in our Milky Way galaxy, we have like roughly 300 to 400 billion stars. And NASA statistics says that each of those stars has at least one planet orbiting around it. So we are basically talking about billions and billions of planets. But as of today, we have confirmed only what roughly 6,000 exoplanets. And there are several ways to find these planets. But before we jump into like how do you find these exoplanets, I just want to kind of like highlight some of the fascinating discoveries that we have um, 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 blanking out some of the um, discoveries that we have achieved, done basically with both the ground-based and the space-based effort. So I listed kind of like some of the exoplanets here and some cool facts about them. So, for example, like Proxima Centauri B basically is the closest rocky planet to Earth, and it's kind of orbit in the habitable zone, in its habitable zone. We have another planet which basically is 60% larger than Earth. It potentially have liquid water on its surface. We have another planet. We have found another planet where it basically rains molten glass sideways with like supersonic wind. We have another planet that we found with molten lava um, on its surface, another planet with signs of water vapor in its atmosphere. Um, we actually have a real life Tatooine planet. That's how we pronounce it.
Tatooine.
Tatooine planet. Thank you, Seb. So yes, we do have a real planet that actually orbit two stars. Um, we have a planet that has a temperature of 4,000 degrees Celsius. It's hotter than many stars. And in its atmospheres, you can find vaporized metals. And my favorite planet basically is the one where it rains molten iron on the night side. And pardon my pronunciation, I have sore throat, so it's hard for me to talk right now. Anyways, so this is just to give you an idea of some fascinating discoveries we have made with existing instruments. And most of these exoplanets were mostly found with the space-based observatories. But it's a very exciting field. Um, so that's the motivation for our observation tonight. So Subaru has one such instrument called SCExAO instrument, and Seb will talk about it more later. So SCExAO instrument basically it's used to take images of exoplanets. So it basically you point your telescope and the instrument to a star planet system, and it will take a snapshot of snapshot of the whole family, the extrasolar family. So the instrument basically, as I was saying before, you have the telescope in the video on the right side. You're looking at the telescope. And on the side of the telescope, you basically go to the infrared Nasmith platform. That's where in the video you see Julia moving in. And it's Sebastian who took that video, and it's a virtual tour that you can actually find it online later on. So here Julia is walking into the Nasmith at the Nasmith platform, and there you see basically this SCExAO instrument at Subaru. So on the left side, there's another view of the instrument. So you have the light coming from the telescope from the right side of the left image, and then you have like two instruments that we will talk about in detail a bit later on. So this instrument is basically used to take images of exoplanets. And just another fun fact, the weight of the instrument is roughly 1,300 kg, and the average weight of an Asian elephant is 4 to 5 tons, just to give you an idea how heavy is this instrument. All right, and if you look at the label on the left side image, SCExAO, if you open all of these, like, the black covers, this is what you see on the right side. It's just filled with a bunch of optics, mirrors. We have deformable mirrors and wavefront sensors. We'll go into more detail once we're going to show you what are we doing exactly today. I'm gonna now hand over to Hashimoto-san because it's his observing night, and he would now talk about what kind of science we are doing today with this instrument. So I'm gonna mute myself, and I will request Hashimoto-san to unmute and take over.
Yes.
Just
Can you hear me? Can you hear me?
Yes.
Okay, thank you so much. My name is Jun Hashimoto. I am researcher in academia, SCENICA in Taiwan. I came in Japan for observation. So I am an observer, and oops. So left panel shows the Subaru Telescope with me. As Garima introduced, Subaru Telescope is huge, and I'm over here and very tiny. So I am, as I said, I'm observer. So I sometimes operate instrument. Left panel shows the control room of the Subaru Telescope, and I also operating over there, and yeah. So is this one slide, Karima? You will. What is the next slide? Sorry. Oh, now, this is one slide. Now I understand. Sorry, could you go back previous slide? Okay, so right bottom panel is my research shows my research interest. My research interest is planet formation. So this is a picture of conceptual figure of planet formation. So there is a bright star in the upper right side, and forming planet is over here in the left side. And so, please go to next slide, Gaima. So, in general, planet formation is taking place in the protoplanetary disk. Protoplanetary disk is a kind of byproduct of star formation. So in the end of star formation, stars are generally surrounded by the disk of gas and dust. So this blue image is protoplanetary disk with H1 view. And the planet is over here. So briefly speaking, planet formation is that planets eat material from the protoplanetary disk, and however, the detail is still needed to be confirmed. So we are studying the accretion mechanism of protoplanetary disk. And for example, planet may be accreted spherically symmetry in the left panel like this. But on the other hand, planet accretion may take place in the polar infold in the middle panel. So, meanwhile, planet accretion, if planet has a magnetic magnetic field, magnetic field accretion may take place. So we need to understand what is the dominant mechanism. So we are studying these younger forming planet. But the one of challenges for studying these younger planet is the number of planet is very limited. To date, only three younger systems have been known with robust detection. So, for example, PDA-17 system, WISP-2, and AB Omega B system. And you see the tiny point in each system. These are planet. So, yes, thanks, Gamma. Yeah. So, please go to next slide. So, in order to, so we start the intensive program for survey with SCExAO. One of purpose is to increase the such kind of young planet samples. So for this purpose, we will observe 68 M-type star with 12 night of Subaru Telescope. So this will be the first unbiased survey of M-type star in the near infrared wavelength. So I hope to detect more and more younger accreting planet in this observation. So this is motivation for this today observation. Oh, okay. Thank you.
Thank you, Hashimoto-san. That was great. Let me jump back into now explaining a little bit about the instrument itself. And then without much further wait, we'll just jump into showing you all the screens that you see behind me. Sebastian is going to go from one screen to the other, and he's going to explain exactly, all the parameters of the observation. So going back to showing play. Okay, here we are. Okay, moving on. Let me talk to you a little bit about how do we take images of exoplanets. So there are two important things. One thing is something that we call adaptive optics. So let me explain you what AO is. So basically, when you're looking at a star, planet light coming through the Earth atmosphere, the light basically meets different layers of basically different temperature, different pressure, different wind speed, and it kind of like makes the light refract from one layer to the other, and it makes the star twinkle. Just to give you an example, this is the ocean center in Maui, and I took this video to kind of like explain this movement of light effect. It's in the easily it can be explained easily here, where you have the sunlight and you're looking through you're looking underwater, and then you can see like how these big fishes, or these creatures are basically moving and creating water waves, turbulence, and it's making the starlight kind of like dance around at the bottom. And here, if you focus on this image here, and now I found my mouse. If you focus on this image here, excuse me. This is the image, real video taken from Subaru Telescope, and you can see basically uh, when you point your 8-meter class telescope through the Earth atmosphere and you look at a star. This is what you get. It's just like a fuzzy blob of light moving very fast, kind of like similar to what you see at the bottom of the swimming pool. So we use a technology called adaptive optics to basically undo the twinkling of the star. So it basically adaptive optics system basically uh, helps us um, measure the aberrations that the light is going through, and measure those aberrations and then correct those. And for correcting those aberrations, AO systems, or adaptive optics, or AO in short, they use devices called deformable mirror. And you're seeing one here. It's just a piece of glass supported by a bunch of actuators. It's a self-reflexing mirror. So you can actually modify the shape of this mirror to correct for the aberrations that are wavefront sensors in the adaptive optics measure. So that's the goal of AOs. It's a very crude way of explaining it, but we'll go into it in more details once we're going to show you how are we doing. We're going to actually give you the live example of how we are actually correcting the Earth atmosphere. So that's one thing with imaging exoplanets. You want to have a stable and better image of a star. Then the second element is, once you have a crisp image of a star, it's still very difficult to see a planet around it, because planets are roughly 1,000 to 10 million times fainter than their stars. So you actually want to block the light of the star. So that's what we do inside the instrument. The image of the instrument that I showed you before, that's what it all does. It does the correction of the atmosphere, and then it blocks the light of the star. And so this is kind of like an example to show you, again, real videos from on-sky observation. You start with this when you don't have an AO correction. You don't have any corrections. You just see a fuzzy blob of light, and then you go from here to here, where you kind of see a crisp image of the star. This is what you expect. This is the it's called the diffraction limited image that you get out of Subaru telescope. Once you have aberrations corrected and your starlight is blocked, then you basically pass that light to either an imager or a spectrograph. So you can take images, direct images, or you can pass the light of that exoplanet to a spectrograph, which basically splits the light into its different wavelength. And by measuring that information, you can basically figure out the compositions of the planetary atmosphere. So this is again a discovery done by SCExAO instrument, where you see a planet, which is I don't know do you know how big this planet is?
It's a giant gas
Giant,
planet, I
yeah,
believe.
yeah, okay. So it's so so the kind of images we are able to obtain from such instruments are of those planets which are self-luminous extrasolar giant planet. We can't take images of planets of like Earth size, just because of the limitation of the instrument. And it's very hard to see faint planetary signal very near to the star. So here's like just one discovery we are showing, you know, with the observation that we're going to explain you later in a few minutes. Anyway, these are more images taken from the SCExAO instrument here, as Hashimoto-san was just explaining. Here you are kind of looking at the circumstellar material where a protoplanet is actually in formation. So it's not a planet yet, it's kind of creating the material from around the star to become a planet. So SCExAO was used to take an image of a planet in formation. Here's another image where you can actually see a debris disk with it's a fancy debris disk with lots of arms, spiral arms coming out of it. We have also taken a video of Neptune in our solar system as well. Well, now it's time for Sep to join in. I'm done with my presentation, just to give you a little background about what is SCExAO, what does it do, what we are doing tonight. Now we're gonna actually share with you the all the observational control system that you were seeing behind me. And now I'm gonna give it to Seb, and he's gonna, let me actually start sharing the screen first.
Should we take questions?
Yeah.
My bad.
I picked up some questions.
Okay,
Yes,
sorry
we do have questions. We sure do.
we can take a break to answer question, and then we can jump into.
We have the chat here.
Yeah. You already explained already, but
see.
I picked up some questions in the chat.
Um,
Yeah,
okay.
sure, of course.
So the question is, who built the instrument? This guy started it.
Oh, is that Olivier? Aloha,
Olivier.
Olivier.
So, do you want to say something about the instrument?
Yeah, the instrument was built by a group of several people. It started with a small team. We have actually Julia at the summit who built a lot of this, Sebastian, Garima. And then we actually expanded over the years because we started collaborating with also an outside team who built fairly large parts and critical components of the instrument. It's a very international team, a lot of young people, a lot of PhD students also got involved. So and it just keeps going. We keep improving it, upgrading it, and building new capabilities driven by the challenge of observing exoplanets and disks.
I think we have two more questions, which I think maybe you should answer those. What are the very unique capabilities of SCExAO?
What are the unique capabilities? I think we have a couple of them. The wavefront control, so the adaptive optics, the ability to correct for the atmosphere turbulence is a very that's an area that we push very hard. One of the unique capability of SCExAO is to have a very high performance adaptive optic system that can work with infrared source. And actually, this is what we're doing tonight. We're using an infrared wavefront sensor because Hashimoto-san is looking at objects that are very faint and invisible. Most adaptive optics systems use visible light. SCExAO can use infrared light to do the correction. And tonight, that's what we're using. We're looking at an object that's very red, very faint and invisible, and we're using its infrared light to do the adaptive optics. So that's one of the unique characteristics. And then the other one I think is on the back end instrument side. We have a lot of new technologies. Some of them that we're just opening for scientists. Sitting next to me is Sebastian, for example, who manages a lot of the photonics devices that are brand new and really allow us to zoom in with high precision on some targets.
So that question is from Bonnie, and the first question was from Andre.
Yes.
And Bonnie asked one more question.
Maybe you wanna read?
Yeah,
Okay.
please.
So now, again, for you, what advice would you give a citizen scientist who wants to spot an exoplanet? That's your Panoptis project.
Yeah. So one of the techniques actually to find exoplanets is one that's accessible to citizen scientists, and it's the transit method. You patiently look at lots of stars and you wait for those lucky times when the planet passes in front of the star. Um, Professional astronomers, especially with big telescopes, are actually not always the best suited to do this because to find these planets, you actually need to look at lots of stars a lot of the time. And so I actually work on a project, it's called Panoptes, that helps citizen scientists get involved in that by building their own little robotic telescopes to look at lots of stars with small cameras.
And I think next question we all can take. Abhishek is asking how much image processing is involved in generating the images, and what methods are you guys using, such as how much image registration, image reconstruction, and maybe image stacking. Do you want to take a stab at it, Sam?
Me?
Yep.
Yeah, sure. A lot. Yeah, in terms of image processing, we basically spend all night taking images, whether it's just pictures like we are going to show earlier, or like what Garima showed. And sometimes we also take spectra of exoplanets or objects that we're looking at, meaning that we are taking the light and we are dispersing the light to see all the colors using like a prism. So in that case, we also stack a lot of images, basically as much as we can, because the more images we can stack, the more information we can get from that. And there's many techniques that exist to do that. Like I said, just taking a lot of pictures and add them together, or multiple spectra and add them together. And image reconstruction, yes. So like Garima said, one of the things that we are fighting is the turbulence in the atmosphere, but we are also fighting some turbulence in our instruments. And so sometimes we need to calibrate those in order to do image reconstruction and to reverse reverse engineer all the aberrations and turbulence that our bunch is inducing on the image. So we do a lot of reconstruction. That's actually what Seamus and Sandrine are doing right now, hidden in their corner over there. Say hi. Hi, Seamus. Hi, Sandrine. So they're doing a lot of image reconstruction. So it's called PSF reconstruction, PSF for point spread function. So they basically take the images and try to model what the aberrations are that created the aberrations that we see, if that makes sense.
You start your process, I think. One more last question from 12th grader. Huh? Oh, where is what? Yeah. From any show, what advice would you give a 12th grader who wants to be an astro explorer?
That's a great question. I think we all can share an advice with a 12th grader who wants to be an astro explorer.
Don't give up.
Don't give up.
Don't give up.
Be curious.
Yeah, be curious.
Have fun.
Have fun.
Science is fun.
Science is fun.
And it's an adventure. You don't know where it leads you because you're constantly trying to answer questions that that no one knows the answer. I think part of being a scientist is, as Garima said, is being curious and constantly asking questions, wondering why is it that the world is the way it is, the universe.
Definitely, yeah. Don't ever listen to people who say, curiosity killed the cat. Don't listen to that. Just keep on with the curiosity. Also, if you got a local astronomy club, go join them. Go see them. A lot of people have, great telescopes. Go ask them about them. They'll love to share it with you, and it gets you nice and interested. And of course, physics and math, lots of it.
Tomika-san, do you have an advice?
Okay. Technically, so 12th grader must think about what's next. What's next at the university. So yeah, astronomy is fun, and curiosity is most important. On the other hand, you must be understand what's going on. So you need language to understand astronomy. So it means physics and math, also English. So yeah, curiosity plus some math and physics skills, I think.
Thank you.
No, thank
Sandrine,
you.
Sandrine, do you have an advice for a 12th grader?
No, I don't know. Yeah, science is fun, isn't it? That's nice.
James,
Sorry?
do you have an advice?
For
12th grade.
Yeah,
to do what?
to be an astro explorer.
An astro explorer?
Yeah, astronomer.
Yeah,
astro-
I guess just get involved with your local astronomy club. Any after school science clubs that you have, those are always great.
Okay.
Provide opportunities.
Julia, do you have some advice? Up at the summit. Not sure he's listening. Hashimoto-san, would you like to say something?
Wait, he is. He's over here.
There he goes. Come on, Julian.
Hello.
Hey,
Hey,
Well,
Jillian.
I don't know, like we said a lot of things already. Don't hesitate to contact astronomers that can help you in projects and other things. Like scientists are usually very happy to help students.
thank you.
Yeah, I think yeah, be ambitious and yeah, don't give up is important. For example, direct imaging planet is generally very hard. So in previous study, we observed 100 stars, but we only detected a few exoplanets in direct imaging. So yeah, never give up. So this is very important, I think.
Thank you. And I think I'll add one more. No question is stupid. So please don't hesitate. If you have a question and you think it's not smart enough, that it doesn't matter. Your question is important. Okay, so if we don't have more,
There was another question from Christian.
okay. I tried to answer and then I got distracted. I think the question was, how many exoplanets can we really observe with optical telescope?
Mm.
Right?
Yes, that's
So
Christian's question.
yeah. So it's like optical infrared telescope.
Yeah.
So it's very difficult to actually, well, it depends on the observing techniques we are talking about. So if it's direct imaging, then it's very difficult to actually find planets because most of the time the planetary light is buried underneath the residual starlight that adaptive optics is not able to correct. So just to like what I mentioned, like out of roughly 6,000 exoplanets that we know from all the techniques, both from ground and space, we have taken images of roughly, I don't know, like a little bit more than 60 of them. So it's very difficult to give a number. Can we really
Yeah, I
observe?
guess it depends on, it also depends on the size of your telescope. So,
That's right.
you know, the bigger your telescope, the tiniest detail you will be able to see. So if you have planets that are very, very close to their stars, you won't be able to see them, even with an 8-meter telescope. So really what drives the amount of planets that you can see is the size of your telescope and how good of an adaptive optics system you have to correct all the turbulence induced by the atmosphere.
Okay.
Thank you, everyone, for your fantastic advice. And Ian also added a bit more there in the chat. I would like to pause right here and welcome the Shadow of the Scientist founder, Raja Guhathakurtha. Raja, welcome.
Thanks,
Hello, Raja.
Shamika. Thank you very much. And thanks to the Subaru team for hosting this session. You guys had terrific answers to all the questions, including the one about, what it's like to be a scientist and, the aspect of not giving up and being persistent. And I really enjoyed listening to that. The human aspect of it, the mentorship, the people who are in your rearview mirror versus people whose rearview mirror you're in terms of your academic journey. Those are such important elements. And I know the questions about, no question, Garima, you said no question is too basic or stupid. I also find that very often scientific research is not about answering questions, but it's about refining your questions, coming up with additional questions. Because the day we run out of questions, that field is dead. that field is not worth researching anymore. So it's very much about coming up with finer, some cases grander questions based on the ones we have today. Again, thanks to the team. And I also wanted to say hello to Olivier. I don't know if we've met in person, but I think we have a person in common in Noor, right? Noor Scarf is your former PhD student.
That's right. Yes, and now working at UH, right next door to our
Very
building.
much. And she was my colleague at the University of California, Santa Cruz, and we did some wonderful outreach together. But there's an example of human connections that really make, like many disciplines, make scientific research so much fun. Anyway, thank you all. And thank you, Jamika, for organizing all this. It's lovely to see such a big crowd of people at the on a Thursday night, at least Thursday night for me.
Absolutely. Absolutely, Roger. Thank you. Okay, back to you, Garima.
Also, thank you, Garima, because talking about not giving up, Garima has spent the last few days with no voice. She didn't even know if she would be able to talk to you guys today. So thank you, Garima, for not giving up. Thank you for taking your medication. And yeah, just thank you.
Thank you. My pleasure.
Sorry?
All right.
Okay.
I'm going to share my screen. There you guys coming back. Excuse me. Sorry about that. I'm going to share my screen again, and I'm going to hand it over to Seb, who is going to take us from all the screens that we see behind me. And Ian, please jump in as well if you want to talk about the telescope status when that screen comes up. So I'm going to hand it over. There you go.
Yeah. So I think you can, yeah, here. So yeah. Oh yeah, I can do this. So what you see on the screen right now is the status of the telescope. Where is the mouse? The mouse is here.
Oh, it's here.
Yeah, it's here. I found it. So all the screens that you see behind us, I'll show it with my computer. All the screens that you see behind us, we are going to go through them, and we're basically using all of them during the observation. There's also a giant screen that you can see right there, which is the Zoom that we have with our observers from Mitaka and also the people at the summit. So that allows us to communicate with them during the observation to see what we're supposed to do, which target we're supposed to go on, and things like that. So the first screen that we have here is the status of the telescope and a lot of telemetry and environment data. For example, if we go on the right, you have the temperature outside. So on the catwalk right here, you have the humidity, you have wind speed. Humidity is a very important parameter to monitor, because when the humidity starts to be too high, we have to close the telescope. Ian, you want to comment on this?
Wait, so our humidity limit is about 80%. So Mauna Kea has a very, very unique environment, which most of the time allows it to be very, very dry. Like it is right now, we're only at 2% humidity. So my lips are all nice and cracky. But that third screen on the bottom, which I believe I can annotate down here, is the dew point. And if you combine the top two screens, the temperature and the dew point, or the humidity there, you get a nice dew point. And what we want to avoid is we have a really, really expensive mirror. It's a very, very highly customized mirror. So if humidity goes too far up and temperature goes too far down, we'll hit the dew point and suddenly water will start getting onto the mirror, which we really don't want. We can't. It takes a lot of money, a lot of time to close that. So once it gets to 80%, usually we close the dome, we turn the AC on, we make sure the condition inside the dome stays good, as well as monitoring the rest of the environment stats there next to it, like the wind speed, to make sure, because winds can get up. 2 nights ago, we had 90-mile-per-hour winds, or what was that, 40 meters per second winds up here at Summit. So we have to monitor each one of those.
Yeah, thank you. And we also have the status of the various motors that actually drive the telescope. So actually we have a little model of the telescope right here. So essentially the telescope, you can see it here. The primary mirror is supposed to be in the bottom here with another mirror right there where the light bounces back and forth. And the instruments that we're using right now is on one side of the telescope right here. So essentially, the telescope is just rotating like this. So this is the azimuth right here that you can see here. We're currently at 93 degrees. And then elevation, this is the other degree of freedom that we can have. And right now we are at 57 right now. So this is the kind of information that we can get on that. The second screen that I can show you right now is this. So we have a list of targets that are on this side right there. And on the left side, we have a sky monitor camera that shows us where in the sky the target is. So that helps us to choose from which target we want to go to. So for example, if we are on a target that is located where my mouse is, we have to take into account that if we want to go to, for example, this target that is all the way around there, there is a lot of slew time. So the telescope will take a long time to go to that target. So sometimes for scheduling purposes, it's good to first observe a bunch of targets that are, in this region and then go to another target. We also monitor the clouds on this because, of course, if there's a cloud, there's no light, so we cannot observe. So if, for example, there is some clouds that are located in this area, then we're going to favor that area to do the observation. And so once we pick the target that we wanted, we go on this screen right there, which is essentially what we use to drive the telescope. So we say, oh, we want to go to a target, for example, right now, UCAC, and a lot of numbers. And so we essentially just select this line and then click on execute, and the telescope just goes on it completely automatically. And once we are on this target, so like Garima said, the first thing that we want to do is to stop the star from twinkling. So while the light of the star goes through the atmosphere, there's all the turbulence that's happening. And so the first thing that we want to do is use our first stage of correction, which is done in this screen. So right now, we're slewing right now, right? Are we slewing?
I think we're done.
Yes.
Oh.
Yeah.
We just switched over to another target.
Okay. So the target was so close that we couldn't see the slew. So that's very efficient. And so once we get light from the star, so you can see on this camera right here that the light from the star is arriving. You do not see a point because this is what's called the wavefront sensor. This camera is what is going to measure what the turbulence in the atmosphere is and what is distorting the light. So right now what Julian is doing is he is configuring this wavefront sensor. It's called the pyramid wavefront sensor. It's working in the infrared right now. Julian installed it, I think, a couple of years ago. And so what he's doing is that he is starting to correct a first set of aberrations. So he's doing a first correction. And Garima showed you an image of a mirror that was vibrating earlier. This is the mirror that is driven by this system. We can actually see on here an intensity map that is changing with time. Essentially, behind the mirror, you have little pistons that are pushing and pulling in order to change the shape of the surface of the mirror. And what you can see here is the intensity is basically the voltage that you're applying on this piston to move the mirror. So the mirror is moving right now as we're speaking, as we can see here. So once this first stage of correction is done, we go to the heart of SCExAO, which is right here. And there's a lot of things happening on here. I'll just go through this viewer very quickly. We have on the right and in the middle something that we use to monitor the status of our instrument. Like Garima showed, there is a lot of fibers, mirrors, translation stage, and things that we need to move in order to carry the light where we want. So we monitor all this here. This image that you see here, there's no light right now on it because the star is too faint to use this camera, but it's the exact same wavefront sensor that we had previously, that we had right here, except that instead of working in the infrared, so at about 1 micron of wavelength, this one works in the visible. So it works at about 800 nanometers. And so here we can see an image of the star that we're observing. You can also notice a lot of birds right here. So each of our cameras is associated with a bird, with an endemic bird from Hawaii. So here we have the pueo, and here we have our nene, and we have the apapane, and we have palila. So all these birds represents, well, we give them a how do you say, a shout out by giving their names to our cameras. And then what do we have here? Here we cannot see many things here, but Garima earlier showed you a slide where you had the image of an exoplanet. And so this is the instrument that is actually taking the image. Thank you. Yes. So right now we cannot see anything because we are acquiring the data. And as we said earlier, it requires a lot of data to be taken and to be stacked in order to get very good images. Oh, here he goes. So here, this is the last image that we've taken. And Julian, do you want to go through what we see here on Caris? Putting him on the spot.
What time today? He can't right now because he's working on the instrument stuff.
I cannot unmute myself on Zoom.
Oh, for some reason he can't unmute himself on Zoom.
Jamika, do you know if we can unmute Julian?
Julian, yes, I'm on it now. Thank you. Sorry about that, Julian. Let me find you in the participants here. Oh, okay, there you are, Julian. And all right, Julian, you're now co-host and should be able to unmute.
Okay, can you hear me?
Yes.
Yes.
Great. Okay, so yeah, what we see here, those are the Caris frames. So Caris is our main science instrument. Caris is not a typical camera because we're doing at the same time spectroscopy and imaging. And so the images we get looks like this. It's some kind of array of little lines. And if we go on this side, of course I cannot move. All these little lines correspond to spectra put on part of the image. And each of them we can see, sorry, I'm also losing my voice. Each of them we can see 3 bands. Those are bands of light in infrared that we image with Caris. There is J band, H band, and then K band. Those are different wavelengths of light. And in between these bands, basically the water in the atmosphere is absorbing the light. That's why we have a bit of a dark band in between. And so the camera, what it's doing is sampling the image with an array of micro lenses. And then we have a prism that disperses the light so we can see all these wavelengths. And it's arranged in a way that all these spectra don't overlap with each other. And from these images, those are already kind of post-processed. We remove some kind of offset on the detector, and we get what we call here the ramps. And from that, we get this cube on the right. And in this cube, we can use this slider here that I'm moving to scan in wavelengths. And you can see what we see here is the image of the star. we have two of them because we're looking at polarization tonight. And so we have a prism that's called a Wollaston prism that splits the polarization in two. And those two images, so they are of the same star, but just different state of polarization. And when we scan in wavelengths, we can see this pattern is changing with wavelengths. It's actually growing linearly with the wavelengths of light. So if we go back to the beginning of the cube, this is J band, then we have H band in the middle, and then K band here. And what we see, so it's an image from the telescope. We have this pattern that's called a Airy pattern. It's basically created by the diffraction of the telescope itself. The light acts as a wave. And so when we collect it with the primary mirror of the telescope, at the edges of the mirror, the wave is going to interact with the edges and create this pattern that's called diffraction. So we cannot really go around it. We will always have this diffraction pattern. But the fact that we have adaptive optics means that this pattern is very static. It's very consistent between images. We taken several images. We didn't really see a difference between them. And so that's what we want. We want very stable images. And the goal of taking polarization data like this is that you can do a differential between those two images and look at the polarization signal in this image. So by just doing the difference between this side and this side, but we also use other tricks. We have in this window, we have a wave plate. So this is an optical device that's gonna rotate the polarization, and we rotate that optics between frames. And the idea is that we change the state of polarization that we look at on the frames. And so we have a second layer of differential where we can do more differential between the images. And that will give us a better precision on the measurement of that polarization. Yeah, I think I don't have anything else to say. I see a question, yeah.
I have a question. What if there's
Yes.
a planet and if you can see it? Do you want to talk about that? Like how we
So,
yes.
yeah, as Sebastian said, we do a lot of processing to see the planets. We never see a planet directly in the raw images because the planets are much, much fainter than the stars we look at. A typical planet that we look at, the contrast is about 10,000 to 100,000 times fainter than the star that we're going to look at. So it's very, very faint. So we have to do a lot of processing, do a lot of processing using the data. For example, when we scan in wavelengths, we can see that pattern is changing with wavelengths, but the planet itself is not going to move with wavelengths. And so we can use that trick to basically subtract the light from the star, because we know that all of these little grains of light, those are called speckles, they're scaling with wavelengths, but the planet signal is not going to scale with wavelengths. So we can use that trick to do some to remove the light from the star after the fact. We also use a trick that in the images that we take with time, with the sky rotating in the sky, I mean the stars rotating in the sky, the planet is actually also going to rotate in the frames, not because they are on their orbit, because that motion is very small, but just because the sky is rotating and the telescope is tracking. And so we can use that information too, because the pattern is not going to change with time, but the planet is going to move around in the image. And so we can use a trick like that to also subtract even more the light from the star. So this is in the case of very young planets that are very bright in infrared because they're very hot. If we try to look at a planet like the Earth, the contrast is so much worse. It's 10 billion times fainter than the star. We cannot see those planets with our current telescopes. We have projects of telescopes that will go in space to be able to reach this kind of contrast. As we said, we need a very good stability, and adaptive optics provides some of that stability, but it's not good enough to be able to reach this kind of contrast at this point. And so you need to go to space to have extremely stable environment and to be able to do this. So I think that answers one of the questions here, like what would happen if it wasn't stable? We really need that stability to be able to subtract as much as we can the starlight to see stuff around the star. So planets or disks, for example, in this case, what we're trying to do tonight, disk of dust, of gas, things like that. I see a HWO mentioned, exactly. So the HWO is a future mission from NASA called the Habitable World Observatory. And basically the goal is to be able to image those planets like the Earth at a contrast of 10 billion times fainter than the star. So yeah.
Julia, did you talk about the astrogrid?
Oh, no, I didn't. So there's, yeah, we have a pattern in these images. I'm just gonna change the contrast here quickly. We actually have a pattern that we create ourselves using our deformable mirror. So these 4 little dots, this is what we call the astrogrid, and it's basically we have a deformable mirror that we can use to create speckles in the image at a position that we want to and at the brightness we want to. And so you have 4 little dots here that we create with our deformable mirror. And we use that for to be able to calibrate the astrometry and the photometry. In this case, it's not super useful because we can see the star itself. But in some cases, we use what we call the coronagraph that's going to try to block the starlight as much as we can to be able to see the fainter things around it. And this coronagraph is going to block the starlight, so we don't know exactly where the star is and how bright it is. And so using this pattern helps us because the star is always going to be at the center of this pattern. And the contrast between the star and this pattern is always the same.
Yeah, so earlier we were talking about a coronagraph and a mask that we put on the star to hide it so that we can unveil everything that is around the star. This is not quite what we're doing tonight. Like Julian said, we're doing polarimetry. We're basically using the fact that when it's like using your sunglasses, polarized sunglasses. When you tilt your head, you can see things going differently. You can actually see different polarizations as you turn your head, and that's basically what's happening. For example, if there's a disk of dust around the star, it's going to have a different polarization than the star. And so when we subtract the two images that Julian was showing, you can actually see the light polarized by the disk. And actually, one of the images that you showed is exactly that. The image that was taken by Miles. Yeah, this one. The one that you can see on the top right here is an image that we get after getting the exact same type of data that we had tonight. So we subtract the two images in order to unveil the disk, because the polarization of the disk is different than the polarization of the starlight that is coming to us. And so the instrument that Julian was talking about here is working in the infrared wavelengths. So it's above 1 micron. And we have another instrument that is called Vampires. And that gives us the opportunity to talk about another endemic species of Hawaii, the Opeapea. This is the Hawaiian bat. And so this
Can I
instrument,
just
yes,
mention that where is this instrument basically? Just kind of remind people
yes,
that here, let me actually, like, SCExAO is here. This is Caris. So Julien was talking about the spectrograph, the images that he was just showing you the cube. And Vampires, if I'm not mistaken, is where it is.
it's here,
Here? This one?
above,
Above, this
yeah,
one.
right here.
This is Vampires instrument. It's kind of like sits above the SCExAO instrument, takes some part of the light from SCExAO.
Yes.
Okay, now handing over to you again.
Yeah, so inside SCExAO, so SCExAO started as a very small bench, I think more than 10 years ago, and it evolved with a lot of people being doing research on it. And so at the very entrance of SCExAO, what we do is we split the light and we have everything that's visible light, so below 950 nanometers, goes to one bench that is on top of another bench, optical bench with optics like Garima showed you, that only sees infrared, so everything that is above 950 nanometers.
That's where the
So the bottom bench, optical bench here is all infrared, and the top bench right here is all visible light. So this is where the Vampires instrument, the visible instrument, is located.
And do you want to talk about who built Vampires?
Yes, so originally this was a project from University of Sydney. So Barnaby Norris, Peter Tuthill installed these instruments actually in 2013. And it has been not renovated, but upgraded lately by a PhD student from the Institute for Astronomy, University of Hawaii, Miles Lucas, who upgraded the whole Vampires instruments, allowing to get this kind of image that we saw earlier. Where am I going? Am I going the right way? I'm going the wrong way. I'm sorry. This image, yes. So thanks to Miles's upgrades, we were able to start obtaining amazing images in the visible, like this one, where you can see all the details from the disk.
With me, sorry to interrupt you.
Yeah.
Sebastian and Julian, could you mention about the relationship between SCExAO observation and future project HWO, Habitable World Observatory? I received a question from Mark.
Oh, so the synergy between SCExAO and HW?
Yes, yeah.
I think the best that can answer this question is Mr. Olivier. How is SCExAO being used for HW, Mr. Guillaume?
Yeah,
Professor Guillaume.
That's a great question. So there is actually a couple of ways. There is a science way first. We are looking at stars to understand how planets form. So, for example, tonight's program run by Jun Hashimoto is doing exactly that. So we're using the Subaru Telescope to understand how stars form planets, and that's definitely guiding choices for the HW mission. You know, which targets to look at, how should we design an instrument to look for specific features. And the other way, of course, that we're contributing is by validating and developing the technologies that when transform from being used on the ground to used in space will allow for detecting these exoplanets. So it may be surprising to people to realize that actually HW will use adaptive optics as well in space, even though it's not looking through the atmosphere. It needs to use adaptive optics. It will run an adaptive optics not to fix the atmosphere, but to fix the telescope breathing, deformation of the telescope. So the technique are very similar. It uses the same wavefront control techniques, also coronagraphy. There's a lot of talks about using photonics to do very efficient spectroscopy. So the technical solutions are the same, and we are prototyping them and testing them on sky so they become technology mature. Because one of the difference between a ground-based telescope and a space-based telescope is you cannot easily fix and tweak things in space. So you really have to make sure that whatever is on the launch pad in the rocket is technologically very mature. And so we play a big role in maturing these technologies.
Olivier, and
I think, sorry, can I add something?
Yeah.
We also we also help currently with next exoplanet missions in space. There is a telescope that's going to be launched. I think this year they're planning to launch it, called the Roman Space Telescope, and that mission has a precursor instrument inside for high contrast imaging with a coronagraph and with deformable mirrors, like Olivier was mentioning, in space. And the goal is not to reach the contrast that HW wants to reach, but a slightly easier contrast. But the first two targets that's going to be observed by Roman were actually discovered by SCExAO by the OASIS survey. So this is a survey led by Shane Curry, one of our main observers at University of Texas, and Kuzuhara-san, who's at NAOJ in Japan. So we have, the first two targets of Roman are going to be ones discovered by SCExAO recently by Sane and by one of his postdoc, Mona El Morsi. And so, it's we provide targets for this kind of technology demonstration in space.
Great.
Well, that's incredible. I had no idea. Congratulations.
There was also a software question.
Yes, software question from Jim. Yeah, Jim is a software developer, and Jim is curious about the software you're using. I imagine it was written custom for this telescope. Do you know what language it was written in, and what UI framework was used?
There's a lot of different languages.
Yeah.
I think one of the software that we use to control.
You want to unmute, Sebastian?
Oh, yeah.
Oh, Garima, you mute. I don't know.
Yeah. So some of the main software that we're using to like control the instrument and do data processing is mainly Python. I think everybody's using Python. When we want to go a little faster, I think we can code in C, C++. And then all the screens that are behind us to control the telescope. I'm not too sure what kind of language it is. Do you, Ian or Julian or Olivier, do you know what language is Gentoo? Gentoo is the name of this interface.
Well, I know the software itself is just Linux, and then a lot of it sometimes Python for some of the data analysis, some of the graphs. And then just regular Ubuntu.
Yeah, I guess that's another thing from the K-12 questions earlier. In computer science is something you want to be familiar with if you want to do this kind of analysis, because there's just a lot of it, a lot of programming to process the images, but also to control the instrument, to take the images of the cameras. Everything is run by software. We mainly use Linux for our applications, but there's a lot of other things that you can use.
So the programming language is mostly for SCExAO, and in general, I think for mostly like all this stuff is in C and then Python. We start having some people programming in Julia as well. But that's the main languages.
Python, yeah.
Thank you. And many questions. Many questions. And a very interesting question about observation from Baku Christian. It seems that most of planetary systems are around double stars and very close of them. How to make a difference between exoplanets and their stars?
Oh, Ian, you already answered? All right.
Oh yeah, you just finished it right as I did. Correct me if I'm wrong, because I'm not the biggest specialty on this, but a lot of the exoplanets that they are observing when they're doing like a coronagraph style are actually much further out. Garima actually showed on one of her slides there, one with the coronagraph, that the gas giant was somewhere probably around twice the orbital size of Neptune's orbit. And so Neptune is extremely far out. I don't think people realize just how far out it is. And so the fact that there is a gas giant that far out is huge. But in order to block out that much light from the star, you need to, unfortunately, you're not gonna be able to see too much in terms of like the inner planets, so the rocky inner planets. So a lot of what they observe are extremely far out gas giants, but technology is getting better and better. So if you guys want to jump in on how you're able to see some of the closer stuff and rocky stuff, go for it.
Yeah, and also if you take a spectrum of that object, you can distinguish whether it's a star or an exoplanet. Spectrum is useful to differentiate those.
I have a question. How many planets we have found around a binary star? Imaged, sorry. How many planets we have imaged around the binary star?
I don't think we have.
We have not
Correct me if
found.
correct me if I'm wrong. That would be extremely difficult because you're doubling the amount of starlight
I
that you're
mean, to say
trying
the
to.
planets at like further distance, giant planets, beyond the solar system level scale around a binary system. Have you found any? When I say found, have you imaged any? I don't have any. I don't know.
I don't think
Olivia,
so.
do you know? Sorry, do you remember?
Well,
Can you recall?
I very few actually. There's two things at play here. There's three things at play. There's what Ian mentioned, that it's technically harder around double stars for us to look for planets. There's also the fact that we are not looking at random stars when we look for planets. We're looking at stars where we have a clue that there is a planet already, and this clue comes from other measurements, like the wobble of the star, either in velocity or motion around the sky. And these measurements, you can only do them precisely if the star is a single star. So we have a bias at that level. And then there's an open science question, partially open, which we think that there is fewer planets around double stars because it's less stable. It's a less stable environment, and it could actually also suppress some planet formation. My understanding is that is still a bit of an open question. We don't have enough statistics to really nail that one down.
A question for you, Olivier. Are you open to taking PhD students?
Always, we need help.
That's why you need to advertise it here.
Yeah, so we actually work with a lot of PhD students, and that's part of the job because we need to form the next generation. People like me are going to retire in a not so distant future, and we constantly train young people, and it's very exciting. It's a very exciting part of the job because within a few years, we see these young people becoming our colleagues and eventually taking over projects. So that's very satisfying. So yeah, we constantly look for students.
Not only PhDs,
Yeah.
also undergrad students. I'm thinking that there might be some undergrad students from UH and other places that are connected on here. So don't hesitate to bug us. Come see us, send us emails. If we don't answer after a week, send a reminder because sometimes we unfortunately forget to answer. Sorry about that. But yeah, just talk to us, and we're full with projects, and so happy to help in that sense. And I think there was another thing. If
The
you can
question.
share your screen again.
Okay, let me. There you go. What would you
Yeah,
like?
the last tab on internet. Yes.
Oh, yeah, that's right. That's
Yes. So at the summit, we have two live cameras that are running 24 hours. The live camera that you see here, I think it's Tanaka-san, Ichi Tanaka, that installed this camera. So this camera is on Subaru Telescope, aiming at the summit. So you can see the two telescopes that are very close are called the Keck telescope. They're handled by Caltech. We can see on the right side of one of these a small telescope that's called IRTF. It was actually built by NASA to follow the Voyager probe. And then the white telescope that we can see is the CFHT, Canada, France, Hawaii telescope. Directly on its right is the Gemini telescope. It's another 8-meter telescope at the summit. And it actually has a twin in Chile. And the telescope that we can see on its right is UH-88. This is the first telescope that was built on the mountain, and it's as its names is is saying it's a telescope that is handled by the University of Hawaii and has an 88-inch mirror. And if you go to the other tab, yes, we also have this time a camera that is on CFHT, so one of the telescopes that we could see earlier, that is aimed at us, at Subaru. So we can still, yeah, this one, the CFHT right here. So it's aimed at us, and we can see the
Yeah, you can see me
Subaru
waving.
telescope. Yeah, you can see you. I think it's almost like Subaru is pointing at the camera. That's
We're
interesting.
pointing directly away. Yeah, we're pointing directly to the west right now. So you're looking through the rear vents right now.
Oh, through the vents.
So you can
Okay.
actually see a little bit of the telescope if you
Yeah.
zoom way into there. So you can see through the bars of it, you can see the little ring at the top of the telescope, just
This is all I
very
can do.
faintly.
Yeah, and
You did it for
on
a hot
the
second. There you go. Yeah, you can see just a little bit of the ring on that telescope there. But we rarely have the rears open. So
yes,
I recall
we have
there was a tragic fire during the early days of Subaru.
yes, during construction of Subaru, there were 3 construction worker deaths during the there was a fire during the time. So we have a little plaque on the side of the telescope honoring them as well. But it was a hard lesson learned. So it's one of the reasons why Subaru has a lot of the advanced safety office and also policies up at the summit. Was in part due to that at the very beginning. So, and I'll talk a little more on that when it's my turn to present.
Yeah, and on the left of Subaru, you can see so what's called a pu'u, which is a little volcanic coal. This pu'u is called Poliahu, which is the Hawaiian goddess of snow, if I'm not mistaken. It's a very nice place to be, and we're very thankful and grateful that we can actually just even walk up there. It's a huge privilege for all of us to be able to do that. Do we have other questions? I don't see the.
I think I see one question by Abhishek, like he's asking, how can someone collaborate with your team from far away, let's say from Europe, as a citizen scientist, and let's say someone wants to contribute to the project? So I think in terms of contributing, it would be better if you join us officially, depending on your level, as a bachelor student or master student or a PhD student or even as a postdoc. That's the best way to get your hands dirty. If you want to work with us at the telescope, work on the bench, and be a part of the observation. As a citizen scientist, I think it's mostly Panoptis project that Olivier talked about previously. That's the best way to work directly, quickly with Olivier on that project, which, as Olivier mentioned, it's all about transit technique, another way to find the planet. For the exoplanet imaging, something that we do, it's I don't know, you can add more, like how
Yeah,
other ways to
it's usually, yeah, you essentially contact us, say what your interest is, and we usually have a lot of projects and a lot of things that we do. If you want to go on the website of the SCExAO website, you can see all types of instrumentation that we're doing, all the techniques that we're developing. And if you're either specialized or curious about being involved in one of them, you can contact us, discuss with us. You were mentioning Germany, I believe. We collaborate with people from anywhere in the world, and it's relatively easy to do because the instrument that is so located on Subaru that you can see on the image right now is accessible from anywhere in the world. So we have lots of collaborators in France, for example, and a lot of them just log on their laptop from France to do some experiment on the instrument that is inside the telescope. So for example, yeah, we also have people from California. Later tonight, we're going to do some testing, and people from the University of California in Los Angeles are going to join to test some of the instrumentation that we have on SCExAO. So really, it's basically contact us, and we can discuss. We can discuss through Zoom. It doesn't have to be formal, and then we can find ways to collaborate. Hey, the sun is rising in Paris. Nice. At least you have sun and no clouds. Do we have any other questions?
I don't believe so, Sebastian.
Browsing through it, yeah. Do you want to check what's happening with the our air correction?
Yeah, so
Loop
here
seems to be struggling. Is that true?
yes, so this loop is not open. You can go on the
Which
one on the
one?
left. Yes. So the loop seems to be okay. We can see that the image is still here. So that means that we can still see the star, and the adaptive optics system is still working. Oh, and we forgot this little bird.
Which one? Oh, this one.
Which one is this?
Is it Amaki?
Oh my God. Is it Amaki? Julian.
Probably. Maybe Julian knows. What do we have?
He's just
EV?
coming back on now. He stepped out for a second.
Yeah, so we have
EV.
EV down here, and
This could
this
be
one-
Amaki. Could be.
Oh my gosh, I'm in trouble. I should know that.
Iki, yeah.
Are we talking about the one on top?
This
Yes.
This is the Elepaio,
Elephant. Okay.
Elephant.
Sorry, my bad.
Sorry.
a small forest bird on Mauna Kea.
At least I got one right.
EEV, yeah.
So if I look at on the SCExAO image, the loop seems to be struggling. So this
Yeah,
kind
so
of
here what we actually can see what the
is a low wind effect.
what the system is doing on here is it's trying to
Yeah.
keep the star center on a point on the Apapane camera. So you can see that it's not exactly on the center of the cross, but we want it to be specifically at the position at which it is right now. And so Olivier has a control. It's called a control loop. So it's a process that takes all these images from Apapane and is measuring the position of the star and is trying to correct a potential displacement of the image, up, left, down, or right. And that's what you see where the mouse is right here. Is we're applying a ramp. We're applying a tip and a tilt on the mirror to try to keep the star centered, because the star has a tendency to kind of drift away, either because of some of the instruments that we have in the telescope with things that change with temperatures and things like that, or just because of the atmosphere that is just applying some random tip tilt jitter, it's called. So we have a loop right now, a process to try to keep the star centered. And that's actually very important for the kind of imaging that we're doing right now. We're taking two images and we want them to be centered the same way during the whole sequence in order to do an efficient differentiation between the images.
And I can add that, like, if let's say there was a coronagraph at the center, which is used to block the light of the star, under this condition, it would not be doing a good job, because if your star is moving around in X and Y, and so it's not fully aligned behind the coronagraph, so the starlight wouldn't be completely blocked or fully blocked. So you would have like a lot of starlight leakages in your final images, and that would potentially block the potential signal from a planet. So such kind of movement and tip tilt is not good. When we
I mean,
want
it's not that bad, Garima. Like what we see right now, the frame rate of this camera is much more than the science camera. So yeah, you see more of the jitter, but it's actually not too bad, I think.
But I think it would depend on the type of chronograph you're using. For the
Yeah,
Leo,
of course.
yes,
No, I
but
mean
for
any vibration is an issue, and we have some telescope vibration that we correct. That's the mainly what's happening right now. The telescope is vibrating a bit, but our loop is trying to keep that stable. It's doing a decent job, I would say.
if you have a sensitive chronograph, that would be still an issue.
Yes.
Well, the key tonight is we're looking at faint stars, right? Our system is optimized to look at very bright stars, but tonight we're looking at stars that are quite faint, and so the correction is not as sharp as if we're looking at a bright star, but the correction is actually quite good, especially for this brightness of stars. And maybe we can go back to the Caris image to see what it looks like. It's this is
Sorry, my bad. This one.
yeah, I mean this is looking good, especially for a star that's quite faint. And actually, the star is so faint that invisible we can't really do much except so all the correction is happening in infrared. The measurement is happening in infrared, and the correction is quite good for such a faint star.
Do you want to say, Olivia, a little bit more on why do you say it's looking good?
Yeah, I can see that by eye. So if we look at the center, we can see a very small spot, and that the size of that spot is as good as it can get. It's limited by the diffraction theory. We call this the diffraction limit of the telescope, which is basically driven by the diameter of the telescope. And so the image is just as sharp as it can possibly be, and it looks quite stable. So when we see an image refresh every minute or so, it looks quite stable. The 4 spots around each of the 2 images also look very sharp. So that's what we're looking for, is those spots being sharp and small, and yeah, it looks quite good. I mean, if it was a brighter star, it would look even better, and then we would put a chronograph.
There was a question. Maybe Kumiko, you can answer from Anne about the night of the 2nd of March.
Kumiko-san?
Yes.
There's
There was a question for you from Anne.
From Anne?
Yes, if people can join during the night of March 2nd.
March 2nd. Oh, thank you for asking. So we plan. Oh, okay. Yeah, March 2nd, the total lunar eclipse, we plan of live streaming. So in few days, so the March 2nd is next Monday in Hawaii. So before Monday, we will send an announcement of like YouTube link, but from our social media, X and Facebook and Instagram. But if you can't find any link, please just visit Asahi Astro Live. It's a YouTube channel of Asahi Shimbun, Japanese news company. So our live streaming will happen at Asahi Astro Live YouTube channel. Thank you so much for asking.
Maybe Kumiko-san, you can type that in the chat.
I think
Yeah,
Jamika did.
Okay, I see.
Oh, she sent the live to the Asahi Astro Live.
Okay.
Yeah.
Wonderful. Thank you.
Thank you.
I think there was another question. I saw a question, but may I ask what skill sets do you accept from a student joining you, say a master student? I think we are looking for a very broad amount of skill set. So when you work in the telescope, whether it's on the telescope itself or on the instrument, there's basically every single type of engineering that you can think about that is required. That goes, mechanical engineering, electronical engineering, optical engineering, software engineering. So any type of skill set that you have that involves, I guess, physics is acceptable. So if you're a student that is in a master's program or even an undergrad program with a major or minor in physics, astronomy, engineering, computer science, and maybe other things that we are not thinking about, but that could be completely relevant. Those are all acceptable skill sets. Oh, so it is sunny in Paris. Nice. So here what we can see, so the screen on which Garima is, this was the screen where we were choosing the target that we want to go on, but we also use this screen, this interface, to record the images on the instrument. So you can see the name on the top of Caris, and you can see a line that is in green on the bottom, kind of in the bottom, that says get object, exposure time object with exp time equals 60. So right now it says that it's taking images with an exposure time of 60 seconds, and nramp equals 100 means that there's 100 images that are programmed to be automatically taken. And right now we were at image number 15, and we are now at image number 16 on this acquisition sequence. We also use this screen not only to point the telescope and to record the images. If you look on the left-hand side of the screen, this is the GUI, the interface that you use to pilot the adaptive optics system that is in the infrared. So the first stage of adaptive optics that we have at Subaru is controlled here, where you essentially set what strength of correction you want to put with what's called the gain. So you have the DM gain right here, and then you can either close the loop in order to activate the correction, or you can open the loop. You can stop the correction, so it stops sending tension on the deformable mirror. And sometimes you want to do that very quickly because, for example, if there's a cloud that arrives and there's no more light, then the wavefront sensor, our system is going to go bananas and is going to send very random and bad voltage on the deformable mirror. And so we want to stop that as fast as we can. And so it is from this interface that we do that. Good night, Andrea.
Yes, Andrea, thank you so much for joining us, and perhaps we'll see you in the live stream that Subaru's doing on Monday for the lunar eclipse. But we also have 2 more Subaru sessions coming up on the 11th and 13th of March. So check out the Shadow the Scientist webpage or the Subaru Telescope webpage for more information. Thank you so much, Andrea.
And I guess one of the screens that we didn't mention and we couldn't show you is a screen that is right here. So this screen has cameras inside the dome of the Subaru telescope, where we can essentially, oh, you can go there actually. Oh, that's nice. So you can see,
Where are we looking at?
you can see here a live image of inside the Subaru telescope. So the primary mirror is right here. So the light arrives from the top, and then the light bounces on the primary mirror and goes on this secondary mirror right here. And then the light goes back down here, and there is a 45-degree mirror that is at the bottom here that sends the light on the right-hand side here. And SCExAO, the instrument that we're using right now, is behind that wall right here, I think. And we have also other cameras inside the telescope to make sure that everything is working properly, that inside the telescope there's no light. The lights that you see here are not inside the dome of the telescope, they're in other rooms of the telescope. But
I
that's
can
also.
actually screen share those cameras if you want me to, or some of them.
Oh yeah, go ahead.
That would be good. Let me.
Grima, if you can stop your screen sharing.
Thank you, Ian.
Go.
Yeah,
Floor is
let me-
yours.
Yeah.
Yeah,
Yeah, so-
actually, Ian is the responsible in Subaru right now. So Ian, maybe you can talk about what you do and why did you become a telescope operator and what your job is.
And
Yeah,
one more
of course.
question. One more question. What's the most difficult part of your job?
Okay, well, so of course, you met me at the very beginning. My name is Ian, though. I'm a night operations assistant up at Subaru. I've got an undergraduate bachelor's in science and astrophysics and astronomy. I decided to become one because I want to get into the field of astronomy and astrophysics. I want to, a little bit before becoming a grad student and grabbing a master's and a PhD. I want to work with some of the other instruments here on the summit of Mauna Kea. I want to kind of get more into the field. I want to also get my own papers out too, which takes a little time. Unfortunately, astrophysics and astronomy is one of the fields now where you have to have a published paper before applying now. So, yeah, so, and it gives me a great experience. Mauna Kea is one of the most unique environments in the entire world. It's one of the best places in the world to view astronomy. It's also just an amazing cultural place too. It's just a fantastic place. I mean, it's really difficult though. Some of the most difficult things about this is you're at 4,200 meters. And so that means up here, there's about 60% less oxygen than down at sea level. And it's also the one place in Hawaii where it snows and it's freezing cold every night. And if I go to here, like they showed off some of the cams, you can see that we just got some big snow just this weekend. It's already starting to melt away a little bit, but you know, it gets really hazardous up here. So I'm also my specific job, like what I actually do, kind of comes in three parts. As one, I'm in charge of the telescope, so I'm the one who actually opens up the dome, opens up the screens around to make sure that all the drives are on, make sure everything is ready and set and prepped for the astronomers and the support astronomers who are observing that night. Two, I also do the troubleshooting. So anytime there's something that goes wrong with the telescope itself, that's not directly instrument related. That's my job. So, you know, if something goes wrong with some of the drives or the shutters themselves, that's me. I got to go to the top of that shutter at the top of there and fix everything up there. And then three is safety. I'm the safety manager up here. So Subaru gives us emergency response training so that if something were to happen, I'm able to help out and evacuate people down. Also look for signs of altitude sickness because we are above 9,000 feet, which means you can suffer from high altitude sickness, which can lead to pulmonary edema or cerebral edema. But as long as you've got oxygen, which we always have portable oxygen up here, and these little packs that we can carry around, connect up. Things become a lot easier up here. But I would highly suggest this type of job for anyone who is graduating from undergraduate in astrophysics and astronomy. All the telescopes up here need operators. Only a couple of them still send operators up to Summit though. Subaru, which is of course this guy, Keck, and IRTF. They're the only ones that send operators up to Summit anymore. The rest of them, they all observe remotely from Hilo or Waimea. So you still get to live in Hawaii if you work for them, but if you want to come up here, then you got to work for Subaru, Keck, or IRTF. And it is absolutely amazing, unique. You get a lot of hands-on experience. You get to talk with people like Sebastian, people like Olivier, people like Julien, and all the graduate students they work with too about how they work and how they go and how their experience was. So it's fantastic. I would also suggest if anyone is wanting to come to the Big Island and come visit Mauna Kea, unfortunately, we don't want you coming up here in the middle of the night, one, because of safety, but two, because we don't want car lights in the middle of the dome. But if you do, there's an amazing website, Mauna Kea Weather Center. If you just search MKWC, it's usually the first thing that pops up on Google. But this will give you a forecast because conditions can get very hazardous here. So you can see things like the fog or the precipitation that is coming in later in the week, and also some of the winds that might be coming in as well. They'll close off the road to Mauna Kea if the road is severe, if there's ice on the road. And you also need a four-wheel drive to come up here too. So if you are planning on coming up here, make sure to double check the weather, make sure to double check your reservations. But this website is also amazing too, because over here on the current condition side, you can go to the webcams and you can see different cams from each one of the telescopes. Gemini has a particularly really good camera that you're able to see. So this is pointed over at Hilo. And in fact, this also gives you a really cool opportunity to see some of the weather. So one thing that's great about Mauna Kea and reason why we love it to observe is we have this boundary of hotter air that comes and rests on top of the mountain, and hot being freezing, but it's hotter than usually the air is at this temperature, which keeps the air from rising above that layer. So it keeps all these clouds down here, almost like a sea. So we get nice clear nights like we're seeing right now, like we can see on our all sky cams over here. Where if we don't have any clouds, don't have anything, it's a really nice night. The seeing is really good too. So yeah. But some of the other unique views that we get to see, this is from Keck's point of view as one of their cams. Only we are able to see it from being up here on our servers. But you can see there's our telescope there. We've got all these vents open to allow the wind to be able to blow in. It cools down everything. We like it to be cooler on the mirror, on the instruments, on everything, because the less heat that you have, the less energy you have in the atmosphere. You have less electrons moving around. You have less water moving around. So the photon that actually goes from the top of the very top of the telescope down and bounces a couple times, we want it to interact with the least amount of things as possible. So we want it to be cool. We want it to be calm. We don't want there to be a lot of water. So that's why Mauna Kea is absolutely amazing for this one.
Thank you.
Check, there was some chat.
Thank you very much, Ian. I think one thing also that we can talk about before the end is I think there's a lot of students that have logged in today. Garima, what studies do one need to do to work in astronomy? What studies did you do, for example?
That's a good question. I did my bachelor's in information technology, not because that's what I wanted to do, is because I did not know how to get into astronomy because I wanted to do astronomy, but I didn't have enough guidance. So I started with a bachelor in IT, and then I moved to France to pursue a master's in astronomy, but I didn't get into astronomy, like core astronomy courses because of my IT background. I basically did my master's in French without knowing the language in astronomical space-based system engineering, same master's that SEP did. And then after that, I basically got into PhD with Olivier and on SCExAO. That was 10 years ago, more than 10 years ago now. So it was a bachelor's in IT, then master's and PhD in astronomical instrumentation. That was my journey. And bachelor's was in India. I'm from India. So just to be clear on that. That's me.
And so after your PhD, what do you do?
So after PhD, normally you are in a position where you want to prove yourself as an independent researcher. So you do something which is called postdoc. So postdocs are basically from 2 years to 3 years. And I ended up doing 3 postdocs because I did not know which country to call home. So I worked for JPL for 2 years, and I worked for Paris for 2 years, and I worked in Canada for 2 years. Then I moved to Gemini and worked for Gemini for 3 years. And then I moved to Subaru 2 months ago. So I've kind of like moved around a lot. And but this is not a typical journey. You don't have to do 6 postdocs. That's just because they're not the only few places on the planet where you could actually work on such a technique, such a technology. And so I kind of like chase the technology. So that brought me to different countries. But you don't have to basically have such a difficult journey. But yes, that's just me.
Nice.
Do you want to talk about
Me?
you? Yeah.
Sure. So I was interested in astronomy very young, and I did some internships when I was actually in middle school. So I was maybe 13, and I did an internship in Paris Observatory. And the people over there told me that if I wanted to work with instrumentation in astronomy, I had to do well the masters that Garima was talking about. There were students back in the day that were in the restaurant, I remember, and so essentially, I went to the university after my high school. I did a bachelor in applied physics, and then first year of master's in applied physics, then the same second year of master's as Garima in space engineering. And then I did my PhD. I actually came in Hawaii, where I met Garima more than 10 years ago now, during my master's degree to do an internship here with Olivier. And then I had my PhD. I came back here as a postdoc 8 years ago, and I was a postdoc at SCExAO, and then I jumped to UH Hilo, where I now I'm a faculty over there. Ian, I think you've been to UH Hilo, right?
I graduated from UH Manoa and from the IFA program over there, but I also went to IFA Hilo for internships. So if you're in California or Hawaii, there's an amazing internship program called Akamai program. And they work a lot on engineering, but it's with all the telescopes up here on Summit. They'll offer you an internship over the summer. You can do it all the way until your senior year or the year you graduated. And it is fantastic. It gets you into the door. It gets you some good networking as well. I thoroughly enjoyed my time at UH. UH Manoa has a bachelor's in science and astrophysics and astronomy. That's typically what you do before you go on to grad school, is you want your a bachelor's in science. But they also do offer bachelor's in arts in astronomy, and so does UH Hilo. Those can also set you up for a good job up here on Mauna Kea, but those are a little bit more general degrees as well. IFA or UH Manoa is a little bit unique because of the astronomy center here, where you could technically go from your undergraduate at UH to your graduate at IFA, all kind of in the same institution. Though sometimes that's not recommended, just because it's good to go to different regions in the world. Different regions specialize in different things, right? Right. Like here in Hawaii, of course, we have the mountains, so we have a lot of instrumentation. And we also have a lot of world-class observation. But France does some amazing instrumentation work. They're kind of at the forefront of there, hence why half the people here are French on this brand new instrument. But there's different locations on the West Coast and East Coast. They all have different kind of specialties. So it's just about kind of researching the college that you like and what you're interested in. Maybe you're interested in cosmology, maybe you're interested in exoplanets, maybe you're interested in plasma. The field is very, very, very large. So when you say you just want to study astronomy, you'll eventually kind of narrow that down to a specialized field. Maybe instrumentation, maybe exoplanets, or for me it was cosmology. So but yeah, just I started out young too. And I came all the way from Florida and came out to Hawaii because I wanted to get on these telescopes so much. And yeah, just lots of physics, lots of math, and just stick with it. It's hard. You're gonna have a hard. You're gonna fail an exam, and you're gonna have to learn quantum, and it's gonna break your brain. But if you stick with it and you're dedicated through, that's the most important thing. Yeah, I just keep on to it.
Hashimoto-san, what about you? I would like to know your journey.
My journey, yeah. So during my university student, I'm interested in searching for alien. So then I visited to previous my supervisor Motohide Tamura, who is retired recently, and at that time, he was searching for exoplanet. So I joined him team as a graduate student. yeah, then during graduate student, I found this field is very exciting and interesting. So I decided to become a researcher. So I maybe 15 years ago, I graduated. I got a PhD. Then I continue search for exoplanet. And yeah, but currently we can observe only gas giant planet. And but in future, maybe yeah, as discussed in this session, HWO, Habitable World Observatory, will be realized, and then my dream will come true, hopefully. So I want to alive at that future. So.
And coming back to the observation, what's your next step? Would you like to share like what you're looking forward to? Like after this observation, I know you have some more observations to go in your program, but what's the end goal of your survey? Would you like to remind us again?
Okay. Okay, so currently we discovered some gas giant planet around relatively massive stars. For example, solar mass stars or more massive stars. So my plan in this project is to find gas giant planet around lower mass stars. For example, 0.05 solar mass star or zero point 0.1 solar mass stars. So this is the final goal in this project.
Okay. And I just want to thank on behalf of everybody here for letting us use your science night and basically, allow us to explain how SCExAO works. So thanks to you, Hashimoto-san, for letting us use this time. So we're very appreciative of that. Thank you.
Thank you very much. This is a very nice experience for me. Thank you.